with in the math region of beryllium, calcium, and oxygen. So, Professor Guy, be welcome.
We share the microphone?
Yeah.
I guess we share the microphone.
Oh, yeah.
Okay, thanks. I will also have my own timer just to make sure that I'm on time. Yeah, thank you, Rula, for inviting me and also saddling me with the task of giving your talk. So this will be a combination of theory and experiment. I thought I will just show you my home. You can come here by plane, by train, but most important, you can come by boat. I warn you, if you come, you may not want to leave. So this is the title of my talk, Algebraic Cluster Model and the Cluster Shell Model. These are basically new developments, and here in Mexico, you actually should be proud. This is one of the centers where this work has been done. Essentially, all the work is a collaboration between Franco Iacchello and Rudolf Beiker. As I said, I will try to do both. I will try to cover the theory, and this is the theory as applied the algebraic cluster model to beryllium 8, carbon 12, O16, neon 20, etc. The symmetries that are involved in here, and then develop the cluster shell model, which is basically adding a neutron to the n equals Z nuclei. Then we will delve into an area where there is phenomenology quite a lot, but not yet fully theoretical formulations. So I hope that you will get enough excited by the phenomenology that I will show you that you might choose to develop the theory for that. On the experiment, of course, there is the experiment that we did with the TPCs at the University of Connecticut, the first evidence for this 3H symmetry, and furthermore, the future search. So let me start from the very basic. This is basically a talk about molecular physics. Molecular physics is characterized by excitation of the distance between the two constituents of the molecule. So we assume that the benzene is inert and certainly the argon, and all the excitation are in the relative motion. Since the 1970s, nuclear physics has been exposed to algebraic models. So let's try to understand what is it. So this is the algebraic model. The first one that we all know is the IBA, and that's the algebraic model of deformed state. A deformed state, in the intrinsic system, angular momentum is not a good quantum number because it's not spherically symmetric. It's only when you rotate, so all states of angular momentum are degenerate in the intrinsic state. Only when you rotate this state, namely move from the body fixed frame to the laboratory frame, you create rotational band and states of good angular momentum. The deformed state, according to Bohr and Mollison, is defined by three variables: the three Euler angle, the deformation beta, and gamma. Since we have 5 variables, it turns out that the group that will describe it is U6. You shouldn't be too intimidated by this statement. All we're telling you is that the Hamiltonian that describes this system is written in terms of the Casimir invariance of the U6 group, okay? Now we move to molecular state. In molecular state, if we have two components which are not identical, parity is no longer a good quantum number. This is not symmetric under parity. Angular momentum, as we said before, is not a good quantum number. So now all states of different parity and different angular momentum are degenerate in the body frame. It's only when you move from the body frame to the laboratory frame and rotate the object that you get rotational band of mixed symmetry. We are always talking about k equal to 0 and k equal to 1 minus as two different bands. In molecular physics, this is the same band. Now, since we have basically a vector, it described as 3 variables, then 3 plus 1 is 4. That's the group U4. So the important point that in this model of molecular physics, parity plus and minus are degenerate in the intrinsic system. And in the laboratory, you will see both parities involved and we'll see parity doublets. It's a major prediction of molecular physics. So if you now try to expand this molecular state in spherical harmonics, now this may sound a bit strange. You use spherical harmonics to expand a deformed state, but that's all right. Spherical harmonics is a complete orthonormal basis. Anything could be expanded. So in fact, Yoram Al-Chassid, George Birch, and I, in 1982 was my annus mirabilis. I published 4 physical review letters in a period of 11 months. This is one of them. The main thing of this paper was to derive cluster sum rules. But we also expand the molecular state, the very deformed state, in terms of the spherical harmonics. And because we have the neck between the two particles, it requires all L values, L equal to 1, so Y1, Y2, Y3, Y3, Y4, all of them are required in the expansion of the molecular state. In that sense, it's different than what we know over here. Over here, only the 1, 2 contribute, and in the expansion of molecular state, all of the multiple are contributing. Therefore, we expect enhanced E1, enhanced E2, enhanced E3, enhanced E4. Parity doublet, mixed parity rotational band, and enhancement of all the multipolarities, completely different object than we know in nuclear physics. So how do we describe in this model a 3-body? A 3-body in a triangular shape will be described by the 2 Jacobi variables, lambda and rho. If you describe lambda and rho in space and time, you describe the molecule. This has been done already in quite a few places, but it turns out that this object has a lot of symmetries. It has to obey a lot of symmetries. First of all, the permutation, the C3 or S3, whatever you want to call it. So this is a rotation by 120 degrees. It has 3 reflection symmetry and horizontal. This is what we call the D3H symmetry. Now, already in the year 2000, I'm quoting over here 2002, Franco Iachello and Roloff Biker were very brave to say, this is what we predict for a 3-body spinning top, for example, carbon-12. There should be the K equal to 0 bond, and there should be the K equal to 3 bond. The K equal to 2 is missing because it's not invariant under C3. You cannot rotate by 180 degrees and get the same. And this band should be the 1 band. In other words, we should see 0 plus 2 plus 3 minus 4 plus and 4 minus parity doublet. In a rotation band in nuclear physics, 24 years ago, they predicted there should be parity doublet. Never seen before in nuclear physics. And then there should be the breathing mode in which the 3 particles will be in an S state and will do the breathing mode. That's what we will call later the Hall state, and then there is bending, etc. This paper sat there completely untouched till I went to Iachello's 70th birthday, which is in Kokoyok. I really wanted to go to this conference. I measured the 2+ state in carbon-12. I thought nobody will be interested in this, but at least I can come and honor my friend Franco Iachello. To my great surprise, I was introduced to this algebraic cluster model, and life has not been the same ever since then. Let's see, 70th birthday, and Franco is now 83. So this is a 3 years tour, which basically started by complete accident. I said, well, I'll talk about some state in carbon-12. That state turned out to be very important for this model. Okay, so moving to the experiment. We need to measure at very high excitation. How do we do that? I will not talk in great detail, but I will tell you about a completely new way of doing nuclear physics, which we have developed. The basic thing is we have an optical readout TPC. And in the optical readout TPC, we have CO2, so we can measure excitation of the carbon and excitation of oxygen. We excite the CO2 with gamma rays. How do we produce them? This is called the high-intensity gamma source, the Higgs at Duke University. In this facility, electrons are running in the ring, almost 1 GeV, and they undulate. When they undulate, they emit electromagnetic radiation. So then the electromagnetic radiation is bouncing back from the mirror, bouncing back from the second mirror. When it comes to this point, the electron comes back and they undulate together. This is what we call free electron lasers. That's how we make free electron lasers. So now the free electron laser is bouncing back and forth. If I send half of the ring another electron, it will meet the free electron laser over here, will do Compton backscattering and give us gamma rays. First facility for nuclear physics for using gamma rays. Absolutely fantastic, okay? Almost monoenergetic. Those gamma rays impinge on our optical readout TPCs, and we measure. We measure track, so this is the distance, it's about 30 centimeters. We measure track from carbon moving to one side and oxygen, and alpha from one side and carbon. This is the photodissociation of oxygen-16. This has been published in Nature, and in fact, DOE sent a news report about this. It's a completely new way for doing nuclear physics. This is what we would call active target TPC and gamma ray. A combination of active target TPCs and gamma ray is a method which we have developed and published. So here is one of the most important things about this method. We have both carbon and oxygen in our gas, CO2. If the photon impinges on carbon, 3 alpha particle comes out. That's beryllium 8. If they impinge on O16, only 2 particles. The topology of this event is very different. So we measure the line shape for the topology of O16 dissociation and carbon-12 dissociation. And the event that fits here and fit here do not fit here. Event which is O16 dissociation does not fit to carbon, and carbon dissociation does not fit to O16. And you can see over here the chi-square plot. Essentially, background-free data. I repeat, background-free data. That's what the TPC is all about. Just to give you an idea, this is at the level of 70 counts. Here, I don't know what to call it. I don't know what to call it, where the background start. 70 to 1, who knows? The basic point is you either have a track or you don't have a track, which you measure in the TPC. If you misidentify the track, That's your problem. You have to get smart. You have to learn how to do it better. But it's not background. It's just a thing that you have to learn. And even better, you can teach your machine to do that. And then the machine will do all this data analysis for you. We're not yet there. I would say we are 80% of the way there. We are starting to use machine learning. Our TPC produced 4 terabytes of data. It will take more than one graduate student, more than 4 years to go over all the data. The machine will do it over 1 week. So this is the take home from our method. We measure without background. Okay, so now in carbon-12, we want to measure state at high excitation. They are broad, they are interfering. The TPC, the second thing that allows us to do is to measure complete angular distribution with 30 data points. You're looking over here on an angular distribution where you measure 30 data points. You can do as many data points as you want as long as you have enough statistics. You can measure at 180 degrees and you can measure at 0 degree. If you try to measure this with gamma rays, they're bulky, they have to move them around. And in the field, when people measure 7 data points angular distribution, it is considered fantastic. Here is 30 data point angular distribution. And they are basically classical example of quantum mechanics. Here is a pure E2, and here is the E1 plus E2 admixture. Pure E2, 0 at 90 degrees, we measure 0, and basically fully symmetric, E1 and E2 admixture, interfering, as quantum mechanics will tell you, this is what you measure. So what we can do now, because we have angular distribution, we can do a phase shift analysis of our data. And the phase shift analysis, our data tells us that we don't just have E1 and E2 amplitude admixture. We have state that are interfering, as quantum mechanics would allow them. And these are the 2 states, 1 minus and 2 plus. So as we go along and improving our system, to measure state at 20 MeV, at 13 MeV, extremely high excitation, you won't see in the data any peaks. All of the information will be in the angular distribution and in the phase shift. Coming back to the theory. The Dish-3A symmetry allows you to connect all the multipolarities. So the B of E2, the B of E3, the B of E4, the B of E6, you name it, whatever you can measure. In carbon-12, they're all measured. And they're all related to one parameter, beta. Now, this is not the beta I've run models on. This is the beta, which is the distance between the center of mass and the participant of the molecule. Beta is essentially the RMS ground state radius. You determine this from the data, and this is a model-free parameter. Okay, so now it turns out, let me go further, that we measure this in carbon-12. Theory tells us that indeed carbon-12, let me just check on time. I think I'm having too much fun and forgetting. Okay, oh, I think I'm okay. So in carbon-12, indeed theory, fermionic dynamical symmetry, asymmetrized molecular dynamic, you name it, all theory tells us, yes, it's a triangle state. So first, our measurement. We measured in this case, we measured the 2 plus. It's a new 2 plus in carbon-12. That's the very 2 plus that I went to Kokoyok and I said, nobody would be interested in this. I'll just tell them about another state in another nucleus. They already heard it so many times. At least I'll have good coffee and honor my friend, Franco Iacchello. Little did I know that that 2 plus is in fact what is predicted by, has been predicted by Iacchello and Roelof, I should say by Franco and Roelof 20 years before. And what we see over here first, in the ground state of carbon-12, we see a perfect rotational band with sequence 0 plus, 2 plus, 3 minus, 4 plus, 4 minus parity doublet as predicted, and 5 minus, all the way to about 25 MeV lying on a perfect JJ plus 1. I think, well, this is clearly the first time such a band has been observed in nuclear physics. So we should stop for a moment and say, okay, victory on prediction number 1, check. But we can do more. We can actually calculate the whole spectrum, and this is what Olaf did in our paper, and we see that indeed we see over here 0 plus 2 plus, but there should be a 3 minus over here, and there should be a 2 plus over here. Those states need to be measured. So we go back to our measurement, say, can we measure at 12.5 MeV, 2 plus and 3 minus interfering? Now we come to the limitation of our facility. Higgs can excite a 1 minus and a 2 plus very nicely, okay? In fact, a 1 minus and a 2 plus interfere. So let me take a step back. We measure the B of E2, we measure all the various parameters. We can rely on them to tell us what we expect. So for interference of A1 and A2 amplitude, interference of 1 minus and a 2 plus, the amplitude are of the order of 1, they are similar. However, the amplitude for A3 over E1 are at a level of 2 to 5% sensitivity. Now, this is a very important point. We are looking on interference of the amplitude. The amplitude the cross-section goes like the amplitude square. So the cross-section itself, there is no hope that you will see a 3 minus in the vicinity of a 1 minus. But the amplitude are at the level of sensitivity of 2 to 5%. It still remains to be seen that this we can do, but we haven't given up. We are still analyzing the data. Certainly, this could be done. 3 minus, we don't know. So last week I was in Croatia. I met a very nice young man from RIKEN. His name is some over here, Masayaka Kimura. He's the new director of the theory group at RIKEN. And he did something fantastic. He took electron scattering data on carbon-12. From the electron scattering data, he gets the form factor. He does a Fourier transform of the form factor and get the transition density. Well, if you have a transition density, you can plot, beautiful plot, and that's what he gets. There is no theory over here except for quantum mechanics, okay? So here it is. This is the shape of carbon-12 that you measure from the electron scattering data. That's the only data that goes in. And he noticed that there are over here areas of very high density, almost as high as the density of the ground state of nuclei, of nuclear state. So I think this is a wonderful example of solid good work, not just relying on theory, but doing what we teach our students, how to go from electron scattering data to what are we looking? Electron scattering is a microscope. This is what you would see if you looked in electron scattering data. Beautiful, beautiful. I was very excited to see that. In fact, if this were to be not PDF, this will be running around and doing all sorts of funny things. But you get the point. I think very nice work. Okay, so in our initial data analysis, and we are really in the initial state, at 13.1, we definitely see an angular distribution which is not pure E2 and not pure E1, but the interference of the two. The angular distribution is not symmetric around 90 degrees. This is in the radian. So clearly we have the E1 and E2 amplitude. But measuring E1 and E2 amplitude doesn't mean that you measure 1 minus and 2 minus state. You need to do the phase shift analysis to actually get the energy of the states, the width of the state, all the various parameters that define the state. But at least we see something which is possible. Moving on, now we discuss carbon-12, which is D3H symmetry. We now add a neutron, and the symmetry is D3H prime. Don't get intimidated by all these words. They're just words. Okay, it's like in the IBA, where we had the IBA for even, and IBFA, which was even plus 1 nucleon. The theory is very clear and has been developed and has been published by Roelof and Franco. In fact, it turns out to be the cover page of Physical Review Letter. I was very happy to see any nuclear physics on the cover page of Physical Review Letter, and this made it. What they did in the same time, they did what we call the cluster shell model. In the cluster shell model, we have this object, the center of mass is over here, and we vary the distance of the alpha particle to the 3-body center of mass, okay? By the way, the equivalent of this in terms of the shell model will be the 3-center shell model. If you want to compare this to shell model calculation, you have to do a 3-center shell model, which is a subject in itself. Anyhow, so as you vary the beta, now beta is not Bohr-Mortensen beta, it's the distance of the alpha particle to the 3-body center of mass. You see the shells are moving around, okay? And they actually determine the beta for carbon-12 from which they get the spectrum. So here we are, all the energies, but let me just concentrate on the B of E2. Again, the whole beauty of this model that the B of E lambda are all given in terms of analytical expression. And in particular, the B of E lambda in carbon-12 in the D3H nucleus, and the B of E lambda in carbon-13, the D3H prime nucleus, are related. And the relationship is written to you over here. Essentially, one Clebsch-Gordan. So the B of E2 are predicted. Here, that's the prediction, and here's the experiment. Aside from the fact that theory and experiment agree, look on the beauty. The B of E2 in carbon-12 is almost the same as the B of E2 in carbon-13. The B of E3 is almost the same. Here's the B of E3. So there's 2 B of E2 and 1 B of E2 and 1 B of E3 and 1 B of E3. And they are different. The B of E2 and the B of E3 in terms of price of unit, they are different by a factor of 3. So you cannot say, oh, it was some kind of an accident. This is the beauty of this model. We can relate carbon-13 to carbon-12 with one simple variable, not variable, parameter, which would be the Clebsch-Gordan. Everything else is determined in the model. Okay, so now we go to beryllium-9. Beryllium-9 will have 180-degree symmetry, so that's C2. So that's beryllium-8, so beryllium-9 will be C2 prime. And here we do the cluster shell model in which we vary the distance between the 2 alpha particles, or to be more correct, we vary the distance between the center of mass and the center of the alpha particle. And the shell model states are moving around, okay? So this will be the cluster shell model of beryllium-9, and here is again a comparison of theory and experiment. Well, I think her first name was Anna. Anna, what was your last name? She's from Argonne. She's not here. Okay. I forgot her name. She gave a beautiful talk yesterday about beryllium. They do the same thing with ab initio shell model. And again, we see this zigzagging of the k equal to 1/2, which is due to the Coriolis, which is well predicted and well observed. However, we must not forget that we are dealing over here with a different, thank you. We are dealing here with a different phenomenon. The figure that you see over here of the cluster shell model and how the shell model states move around due to the distance between the two alpha particles, it may remind you of the Nilsson model. In the Nilsson model, we have the beta of Born model zone, and the shell model cells are moving. But there is a fundamental difference between the two. In here, where we have a deformed state and a neutron running around it, we only predict enhanced BOV2. Remember our paper with George Birch and Yoram Al-Chassid, that all multipolarities should be included in the molecular state. So in carbon-13, we would expect all multipolarities to be enhanced. We just saw E2 and E3 enhanced. And we should see parity doublet, because this triangle is not invariant under parity transformation. Okay? In beryllium-8, it is invariant, but not in carbon-13. So don't confuse yourself that this is another Nilsson model. This is a completely different phenomena, a molecular phenomena that has not been realized in nuclear physics before. Okay, so now we come into the realm of phenomenology, which still does not have a theoretical foundation, and I hope to excite you or maybe antagonize you sufficiently that you will go home and say, aha, I need to build a theory. I need to build a theory to prove that this is all wrong, or maybe better, I need to build a theory because the phenomenology is so amazing. So what about Hall state? Can we look on beryllium-7? Beryllium-7 has two alpha particles with one alpha particle with a hole. When I first talked to Franco, I said, maybe would be alpha star or beryllium-8 with a wounded alpha particle. You know, high energy physicists talked about wounded nucleon traveling through nuclear matter. So can we now look on beryllium-7 as a hole in one of the alpha particles? Well, here it is, okay? Same as what we saw in beryllium-9. It's even more mind-boggling for fluorine-19. In fluorine-19, we see the K pi 1/2 minus and the K pi 1/2 plus. Parity doublet like you would not believe it. 1/2 plus, 1/2 minus. 3/2 plus, 3/2 minus. 5/2 plus, 5/2 minus. 7/2 plus, 7/2 minus. 9/2 plus, 9/2 minus. 11/2 plus, 11/2 minus. Mind-boggling, in my opinion, okay? If you're not excited, I'm sorry. I cannot excite you anymore. To me, this figure really calls for theoretical explanation. Such a fantastic, this is all the state. This is not, I'm not cherry picking over here. And to see such a beautiful parity doublet all the way to 11/2, to me, is mind-boggling. Okay, so if we have Hall state, what about particle Hall? Can we describe beryllium-8 as this wounded alpha particle where now we have particle Hall? Well, we go back to the cluster shell model. We can have a hole in the 1/2 plus and the 1/2 minus, and we can excite them to the 3/2 minus and to the 1/2 minus. That's all our particle Hall. So we can do the angular-momentum algebra. If I excite 1/2 minus to the 3/2 minus, this particle Halls will give us 1 plus and 2 plus. And if I do the excitation from here to here, it will give me 1 minus and 2 minus, and that's it. So what's the data show us? These are all the state known in beryllium-8 below 19.5. I haven't left out any state. All the state that I predict from this simple angular momentum algebra, all the state that I predict are here. Okay, so there is the ground state band, there is the k equal 2 plus, k equal 1 plus, k equal to minus, and k equal to 1 minus. All the state predicted and only the state predicted are observed between 20 MeV and beryllium-8. Now, if that doesn't excite you, I have no hope for you. Well, this is not the end. Those states are predicted to be deformed. They are particle Hall state in a deformed. So they should support rotational band. Well, how does the data look? Here's the rotational band of beryllium-8. Here's the k pi 2 plus. We already know that there is a 2 plus, 3 plus, and a 4 plus over here. This is the isobaric analog of lithium-8. Okay? So we already know that the k pi equal to 2 plus support a rotational band. Those of you who are looking for a good experiment, measuring the B of E2 in lithium-8 of the 2 plus, the isobaric analog of this 2 plus, should be of great interest. I remind you, it's an unbound state, so you have to measure the neutron. We already know that one of this state, which I call particle Hall state, I'm the only one who does it, I call it particle Hall state, they support a rotational band. What about the K2 minus? There is a state over here. And what about the 1 minus? There is a state over here, okay? So, Philippe Page did an R matrix analysis of the 21.5 MeV state, and he claimed that this is a 3 minus. This is published in 2005. Aha, R matrix tells us that there is a 3 minus over here. So is that the beginning of a 2 minus, 3 minus, 4 minus? We have to measure. With all due respect to our matrix, we need to measure it. Okay, so in fact, we did an experiment last November, and this is the 3 minus that we still don't know what is the state. Philippe Page tells us it's 3 minus. We have data in our Isolde measurement on this state. Unfortunately, we requested 11.5 MeV per nucleon. They was worried about going so high in energy, and we only got 11 MeV per nucleon. But it turns out that we do see this state, but we run out of oomph on this state. No justice in the world, really. I mean, another half MeV per nucleon, and we would have seen those. So this will remain a mystery. We do have data on this state, and we would be able to tell you if Philippe Page is correct. If he is correct, we now have the first 2 states in the rotational band. I don't want to badmouth the Isolde. They did a wonderful, even 11 MeV per nucleon is already pushing the machine very much. They gave us the best accelerated beryllium 7B. Our proposal was for 10 to the 6 times larger. And each one of these operators deserve a bottle of wine, not to share. They did such a beautiful, beautiful work. We still need to analyze the data. So to conclude, there is no question in my mind that algebraic cluster model is a new chapter in cluster physics in nuclear physics. The work that Rudolf Becker and Frank Berkel did 24 years ago is now blossoming. I just came from a cluster conference where people are measuring left and right, and they ask, how are we going to interpret it? Algebraic cluster model is the answer. The cluster shell model is an extension of the shell model to molecular orbit, and I think here it is on solid ground. There is centralizing phenomenology of what I call conjecture. I haven't observed, I conjecture cluster shell model, particle Hall state. They are awaiting theoretical formulation, which I hope I aggregated you enough to go home and do the work that needs to be done. And with that, I thank you.
So thank you very much. So folks, now to the questions. Yes.
Thank you. Nice talk about this elastic scattering of the carbon or electron scattering, you say. Could you explain how you got from the electron scattering data? Because I mean, if it is just elastic, say, then you get a spherical shape, and the cluster doesn't come out of any transformation. I mean, you cannot just go from 1 dimension to 3 dimensions easily.
So you want me to explain to you how electron scattering data is analyzed?
No, this I know how it is analyzed. So how do you go from, say, the cross-section, elastic cross-section, which you showed actually?